we want to find the derivative, d by dx, of x to the 2x in two different ways. First by logarithmic differentiation, and second by the so-called stacking method. So for part A, let's do logarithmic differentiation and start with that. For logarithmic differentiation, we write this thing as y equals x to the 2x. Next, we take the log of both sides. I'll do the natural log in this case just because, well, it's more natural. Down comes the 2x, properties of logarithms. So this gives us then natural log of y equals 2x natural log x. And then we hit both sides with the derivative. D by dx of both sides. On the left side, the derivative of natural log y is 1 over y, of course, times y prime. That's the chain rule part. So we have 1 over y, y prime, equals, on the right-hand side, we'll need the product rule. So I'll lump the 2 in there with the x, though we could certainly do it other ways, but I'll do 2x for one term and then natural log x of the other. Well, recall that the product rule tells us that the derivative is a prime b plus b prime a. So we have a prime 2 times b, natural log x, plus b prime 1 over x times a, 2x. All right, so we can simplify that a little bit. 1 over y, y prime is, how about, let's do 2. Let's factor out a 2, and then we're just left with natural log x plus 1 here because these x's cancel out. Finally, we multiply up by y, so it'd be 2y times all that. But remember, y, from all the way back here, y was actually x to the 2x. So when we multiply up by y there, we get y prime, which is what we're looking for, equals 2x to the 2x times the quantity natural log x plus 1. And that is our derivative. Okay, on to part B for the stacking method. There are any number of ways to call this thing, but I've heard it called stacking, so we'll stick with that. But it basically says anytime you have a to the b, you can rewrite this as e to the natural log a to the b. Why? Well, e and natural log are inverses of each other, so they essentially undo each other, leaving us only with a to the b again. So a to the b is indeed equivalent to e to the natural log a to the b. Okay, so we're taking the derivative then, d by dx, of, instead of x to the 2x, well, I'll say x to the 2x. Now I'm going to rewrite this as d by dx of e to the natural log x to the 2x. Well, the good news is now our 2x comes down to the front of the natural log, but not down in front of the e. This is the properties of logarithms again. So here we have still the derivative. We haven't taken the derivative yet. E to the 2x natural log x. Okay, well now we can take this derivative. Recall that the derivative of e to the u is e to the u times u prime. That's the chain rule there. So the derivative of e to the 2x natural log x is e to the 2x natural log x again, times the derivative of the inside, times the derivative of 2x natural log x. Well, we'll apply the same chain rule here. So we have 2 natural log x, that's a prime b, plus 1 over x times 2x b prime a. Okay, well, factoring out a 2 and simplifying a little bit gives us 2 e to the 2x natural log x times natural log x plus 1. Now we'll take this 2x back up into the exponent here, which gives us 2 times e to the natural log x to the 2x power, x, all times natural log x plus 1. And now the e and the natural log undo each other again, and we get 2x to the 2x, all times the quantity natural log x plus 1. I'm almost out of room, barely made it. There we go. And of course, we get the same answer for both of those methods. Which do you prefer? Personally, I prefer logarithmic differentiation. That's my go-to method, but you're certainly free to use whichever method resonates more with you.